There is an airplane sitting in the Mojave Desert right now that is so wide it cannot legally taxi on most of the world's runways. Its wingspan is longer than an American football field. When it takes off, it carries more weight than 10 fully loaded semi-trucks stacked on top of each other. It was built from the bones of 2 dead 747s, assembled almost entirely by hand inside a hangar that had to be constructed specifically because no existing building on Earth was large enough to hold it. And its mission is not to carry passengers, not to move cargo, but to launch vehicles that travel faster than a rifle bullet, 5 times over. This is the Stratolaunch Roc, the largest wingspan aircraft ever to fly. And by the end of this video, you'll know exactly how it's built. Most people who have heard of the Roc assume it is a relic, a curiosity, a billionaire's vanity project that never went anywhere. That assumption is completely wrong. As of 2025, the Roc is fully operational, booked solid through the end of the year, and is at the center of the most important military aviation program the United States is running. The Pentagon has set a goal of conducting 1 hypersonic test flight every single week. The Roc, and the vehicle it carries, is a primary tool for getting there. The U.S. Missile Defense Agency has awarded Stratolaunch a $24.7 million contract. The company completed its first fully reusable hypersonic flight in December 2024, its second in March 2025, and has already conducted a third in May 2026. This program is not a prototype anymore. It is operational. And the machine at the center of it all is the most unusual aircraft ever to leave the ground. The story begins not with the Roc itself, but with the man who decided it needed to exist. Paul Allen, co-founder of Microsoft and one of the most consequential technology investors of the 20th century, had a problem he wanted to solve. Launching satellites into orbit required a fixed launch pad, a specific weather window, and an enormous rocket that could only go to 1 orbital inclination per launch. Allen believed the solution was simple in theory and staggering in practice. Build a flying launch platform so large it could carry a rocket to 35,000 feet, release it in midair, and let the rocket finish the job from there. No launch pad, no weather delays, launch from anywhere, reach any orbit. In 2011, Allen announced the project publicly. He teamed up with Scaled Composites, the legendary aerospace company founded by Burt Rutan, the designer responsible for the first private aircraft to reach space. Rutan had been playing with the concept of a giant carrier aircraft for over 20 years. Allen gave him the resources to actually build it. The budget allocated was in the hundreds of millions of dollars. Construction of a purpose-built facility at the Mojave Air and Spaceport began in January 2012. But before a single piece of the Roc could be manufactured, Stratolaunch had to solve a problem that had never been solved before. Where do you build the world's largest airplane? The answer was, you build the building first. A custom hangar with 88,000 square feet of manufacturing floor space was constructed specifically for the composite wing and fuselage sections. A second building, the carrier assembly hangar, measuring 92,640 square feet, was completed by February 2013. These were not repurposed warehouses. They were purpose-designed structures built to precise humidity, temperature, and clean room specifications, because the material at the heart of the Roc is not aluminum. It is carbon fiber. And carbon fiber is not forgiving. The decision to build the Roc almost entirely from carbon fiber composite was driven by one inescapable constraint: weight. An aircraft with a 385-foot wingspan that weighs too much simply cannot fly. Carbon fiber gives engineers a material that is stronger than steel at a fraction of the weight, highly resistant to fatigue, and capable of handling the enormous structural loads that build up across a wing of this size at altitude. But manufacturing with carbon fiber at this scale had never been attempted before. Workers inside those Mojave hangars stacked carbon fiber sheets at precise angles, vacuum sealed them into layups, and baked them in industrial ovens called autoclaves until they cured into structural panels stiff enough to handle forces engineers described as equivalent to balancing an elephant on a ruler. And a significant amount of that work was done by hand. Now, here is the engineering decision that defines the Roc's entire character, and it is one that no other aircraft manufacturer in history has made at this scale. The Roc does not have one fuselage. It has two. Each fuselage is 238 feet long. They run parallel to each other, connected by a single enormous wing in the middle and by a rear spar assembly at the tail. The pilot, co-pilot, and flight engineer sit in the right fuselage. The left fuselage is unmanned, carrying up to 2,500 pounds of mission equipment and flight data systems. Each fuselage has its own cockpit, its own tail, its own empennage. They are, in structural terms, two complete aircraft merged into one. The reason for this configuration comes directly from the mission. The payload, whether a rocket or a hypersonic vehicle, hangs from a pylon on the center wing section, in the open space between the two fuselages. That placement is optimal for aerodynamic stability at launch and for structural load distribution. But it creates a challenge that no aircraft designer had ever had to solve at this scale before. A twin-fuselage aircraft of this size experiences asymmetric loading conditions that are genuinely unique in aviation. When the payload is attached on one side of center during turns, the aerodynamic forces twisting the wing in different directions at the same time reach levels that simply have no precedent. Every joint, every composite spar, every fastener in the structure had to be engineered for loads that could not be validated against any existing aircraft. There was no comparable data to borrow from. Then there is the question of the engines. And this is where the Roc's builders made a decision as clever as it was unusual. Rather than designing 6 new engines from scratch, which would have added years to the program and hundreds of millions to the budget, Stratolaunch purchased 2 retired Boeing 747-400 jetliners from United Airlines. They stripped those aircraft down to their essential mechanical components: the engines, the landing gear, the hydraulic systems, the avionics, and various subsystems. The engines were Pratt & Whitney PW4056 turbofans, the same units that powered commercial 747-400s on transatlantic routes for decades. Each one produces 56,750 pounds of thrust. 6 of them together produce a combined 340,000 pounds of thrust, enough to push 1.3 million pounds of aircraft and payload into the sky. The landing gear, pulled from those same 747s, was reconfigured into a 28-wheel arrangement, 12 main wheels per fuselage, plus 2 nose gear per fuselage. This massive wheel count is necessary because the Roc's maximum takeoff weight pushes the ground loading to levels that require the load to be spread across as many contact points as possible. One of the lead engineers summarized the philosophy with a phrase that became something of a motto for the project: "We didn't want to invent anything. Wherever proven technology could be borrowed, adapted, or repurposed, it was." This kept costs lower and reduced the risk of novel systems failing during early test flights. By June 2016, Scaled Composites had 300 people working on the project full-time. By May 2017, Stratolaunch had spent hundreds of millions of dollars on development. On May 31st, 2017, the aircraft was rolled out of its hangar for the first time and rested on its 28 wheels without the construction scaffolding that had surrounded it for years. It was the first time anyone outside the project had seen it in full. The reaction was immediate and global. Nothing like it had ever been photographed on a runway before. Almost 2 years of ground testing, fuel system validation, engine runs, and taxi tests followed. Low-speed taxi tests at 25 knots, high-speed taxi tests approaching rotation speed. Each phase expanding the team's confidence in systems that had never been operated together at this scale. On April 13, 2019, the Roc lifted off from the Mojave Air and Spaceport for the first time. It stayed aloft for 2 hours and 29 minutes, reached an altitude of 15,000 feet, and landed without incident. It was the maiden flight of the largest wingspan aircraft in the history of powered aviation. But here is where things get genuinely complicated, because Paul Allen never saw it happen. He died of complications from non-Hodgkin's lymphoma on October 15, 2018, 6 months before his airplane flew. His sister Jody Allen, as chair of the parent company Vulcan Inc., made the decision to let the aircraft complete its first flight as a tribute to her brother's vision. Then, Stratolaunch ceased operations. The company was placed for sale. In October 2019, private equity firm Cerberus Capital Management acquired Stratolaunch and its one-of-a-kind aircraft. And Cerberus made a decision that changed the entire trajectory of the program. Instead of launching orbital rockets, the Roc would become the world's most capable platform for hypersonic flight testing. The mission shifted from satellites to speed. This is the part of the story that most people have not followed closely enough, because what Stratolaunch has accomplished in the last 2 years is extraordinary. The vehicle the Roc carries today is called the Talon A. It is a dart-shaped, rocket-powered autonomous aircraft, roughly the size of a small business jet. It hangs from a pylon mounted on the Roc's center wing, carried to altitude, then released and ignited. The Talon A's Hadley rocket engine, developed by a company called Ursa Major, burns for approximately 200 seconds and accelerates the vehicle past Mach 5, which is 5 times the speed of sound, or roughly 3,800 miles per hour. The first powered hypersonic flight of the Talon A prototype, designated TA-1, happened on March 9, 2024. It was a single-use vehicle, designed to prove the core systems worked before the team tackled reusability. It was dropped over the Pacific Ocean, ignited, reached high supersonic speeds approaching Mach 5, and recovered via a controlled ocean splashdown. Every objective was met. Then came Talon A2, and this is where reusability entered the picture. TA-2 has landing gear. In December 2024, it completed its first fully hypersonic flight, exceeding Mach 5, and landed on a runway at Vandenberg Space Force Base in California. The aircraft was recovered intact, inspected, and reflown. In March 2025, TA-2 flew again, broke its own speed record from December, and landed again. 2 hypersonic flights, 1 reusable vehicle, in under 4 months. A third publicly confirmed hypersonic flight with the Talon A followed in May 2026, this time launched not from the Roc, but from Stratolaunch's second carrier aircraft, a modified Boeing 747-400 called the Spirit of Mojave, demonstrating that the system can now operate from any airport capable of handling a standard 747. The implications of that last detail are enormous, and this is where the full scope of what Stratolaunch is building becomes clear. The Roc is massive, capable, and operationally limited by its size. It requires very long runways and specialized facilities. The Spirit of Mojave, by contrast, can operate from virtually any major international airport. Together, the 2 platforms give Stratolaunch something no other hypersonic testing company in the world can offer: global coverage. The Department of Defense wants to conduct hypersonic tests from locations that simulate realistic threat trajectories. Testing over the Pacific from California is one scenario. Testing from different latitudes, different hemispheres, different angles of approach to targets is an entirely different challenge. With the Spirit of Mojave operational alongside the Roc, Stratolaunch can take the Talon A essentially anywhere. The company is fully booked through 2025 and has already started filling its 2026 manifest. It is under contract to the U.S. Navy's MACH-TB program for 5 flight tests. The Missile Defense Agency is a customer. In June 2025, Ursa Major was awarded a $32.9 million contract to deliver 16 upgraded Hadley H-13 engines to Stratolaunch, securing the propulsion pipeline for the next phase of testing. Here are the numbers that frame the full picture of this machine. Wingspan, 385 feet, or 117 meters, the longest of any aircraft ever to leave the ground. The previous record holder was the Hughes H-4 Hercules, the famous Spruce Goose, at 321 feet. The Roc surpasses it by 64 feet. Empty weight, 500,000 pounds, or 226,800 kilograms. Maximum takeoff weight, 1.3 million pounds, or 590,000 kilograms. Payload capacity, up to 550,000 pounds, or 250,000 kilograms. 6 Pratt & Whitney PW4056 engines, each producing 56,750 pounds of thrust. Combined thrust, 340,000 pounds, roughly equivalent to 5 F-22 Raptors running at full afterburner simultaneously. 28 wheels in total, 2 fuselages, each 238 feet long. Service ceiling, 35,000 feet. Operational speed, Mach 0.63. Range without payload, 2,500 nautical miles. As of May 2025, the Roc had completed 24 recorded flights. It is the only aircraft of its kind in the world. There is no backup. There is no second airframe. There is one Roc. The manufacturing legacy of the Roc cannot be separated from the manufacturing challenge of the Roc. It remains, as of 2025, the largest all-composite aircraft ever built. Everything, from the wing skin panels to the fuselage frames to the massive control surfaces, was fabricated from carbon fiber, cured in autoclaves, and assembled by hand inside those Mojave hangars. The precision required to align 2 fuselages separated by a 117-meter wing, and to ensure that the aerodynamic centerline of the entire structure falls within the engineering tolerances that make it flyable, represents a manufacturing achievement that has not been replicated anywhere else in aviation. The wing itself was assembled in sections, with precision laser alignment tools tracking the relative positions of each structural element as the joins were made. The composite spars and ribs that carry the bending loads were designed for load cases that had no historical precedent. Engineers essentially had to calculate from first principles what forces an aircraft this wide would experience at cruise altitude with 500,000 pounds hanging from its belly, and then design a structure that would survive those forces with adequate safety margins. They got it right. The Roc has never had a structural anomaly in flight. Piloting the Roc is, by the account of test pilot Steve Rainey, an exercise in managing a machine that behaves unlike anything else in the sky. The scale of the aircraft means that roll response is slow. The spacing between the 2 fuselages means that crosswind corrections affect each nose gear independently. Landing requires simultaneous management of 2 nose gear systems, 2 primary gear systems, and 6 engines whose thrust vectors are distributed across a 385-foot wing. Every pilot who has flown it describes the landing as the most emotionally intense experience of their career. There are now 2 fully certified flight crews cleared to fly TED.